Assalamu alaikum. Welcome to the lecture 5th of unit 2nd. Today I am going to teach you one more active load, that is RLE load. This is a simple circuit diagram of single phase half wave uncontrolled rectifier for RLE load. The one example of this RLE load is your motor, where we have back EMF. The current and voltage across this load is represented by I naught and V naught. I have already taught you in the previous lecture that this diode will be conducting only when this Vs is equal to Vr plus Vl plus this voltage E. Or we can say this Vs will be equal to Vm sine of omega t is equal to Ri naught plus Ldi naught by dt plus E. Or we can say the peak of the current will be at that point where our Vs minus E is equal to our Vr. Or we can say peak of the current will be at Vl is equal to 0. This is the waveform for the source voltage I naught, V naught, and the voltage across the diode. Since here the driving force is the source voltage Vm sine of omega t. This is the waveform for this driving force Vm sine of omega t, where we are representing this E by this yellow dotted line. This is not too much clear. This is the yellow dotted line. That means this represents the EMF. The diode will not conduct unless this source voltage reaches this point theta 1, or we can say until and unless Vs is greater than E, the diode will not conduct. Up to that point, that means up from 0 crossing to this theta 1, our diode is reverse bias. Once this diode conducts, once this source voltage is more than this E, our current will flow in the circuit, and this current I'm here, and the peak of the current will lie somewhere between pi by 2 to pi, as this is RLE load. That's why I am showing peak here, and the current will decrease and becomes 0 beyond this pi. The value of this conduction angle depends on the value of this L. The main difference here we can see from the wave shape is that in the RE load, the diode conducts from theta 1 theta to pi minus theta, while as here the diode conducts beyond this pi. That means in case of RLE load, because of that inductor, the current goes beyond that pi. And the value of this conduction angle, since here conduction angle increases because of L, this value of this conduction angle depends on the value of that inductor. Here I am showing the for the first cycle I am showing the value of the current. From this, for the second cycle I am showing the value of current. Since the current becomes 0 at this point, or we can say up to that point, our output voltage will follow our source voltage. That's why I'm showing here this output value, this output voltage, because current is up to this point. We can say that our output voltage will follow this source voltage up to that point, and after that the diode is reverse biased. Since the diode is reverse biased, the voltage across that diode will be exactly, because current is 0, I naught R drop will be 0. That will it will be equal to our EMF source E. Or we can say this will be once in every point here, when the diode is reverse biased, it output voltage will follow the E. As we know that from 0 to theta 1 diode is reverse biased, that in that case also V output will be equal to E. Also here, after this beta angle, the diode is again reverse biased and will follow this E. That means in the next cycle I am showing the conduction from 2 pi plus theta 1 to this angle. If the conduction angle is gamma, we can say from 2 pi plus theta 1 to this 2 pi plus theta 1 plus gamma. What is the voltage across diode? Same, since we know that from 0 to theta 1 diode is not conducting, that means the voltage across diode will be equal to, in the reverse bias, it will be equal to minus E. That means this voltage, the reverse voltage across the diode will be equal to this minus E. against diode is conducting from this is the theta 1 to this pi plus theta 1. After that, diode is reverse bias. That's why I'm showing here that it will follow the source voltage, and the peak of the source voltage will be minus Vm minus E. At this 2 pi, the diode is again at this is a zero crossing of second cycle. We can again say the diode is reverse biased, and the output voltage, that reverse voltage across diode, will be at this minus E, and after that is decreasing. Because why is this decreasing? Because the source voltage goes on increasing, and at this point, that is 2 pi plus theta 1, again the diode is forward bias, and the voltage across the diode will be 0. This is the waveform for this RLE load, or we can say from 0 to theta 1, diode is conducting from theta 1 to this pi plus theta 1. Again here from 2 pi plus theta 1 to 3 pi plus theta 1. In these intervals, diode is not conducting, and the peak of the current will be somewhere where our VL is basically equal to, at this point I'm saying this VL is equal to 0. Since you know the conduction angle, that's from this theta 1 to pi plus theta 1. Accordingly, you can calculate the average output voltage and the average output RMS.
Now, the next topic is phase controlled rectifiers for different types of loads. That means in the previous lectures we have studied single phase half-wave uncontrolled rectifier for R load, for L load, for RL load, for RLE load. Now I will be teaching you single phase half-wave but not uncontrolled but controlled rectification for R load, RL load, for RLE load. In the previous all lectures, the average output voltage once was constant for a given load and the given input. However, here in the controlled rectifier, the adjustable DC output voltage is obtained by varying the input AC voltage, and that V output is controlled by the delay or the switching angle alpha. That means by changing the value of this alpha, we can get the adjustable output DC voltage. Now the first type of load that I am using is the R type of load. That means I am teaching you single phase half wave controlled rectifier for R load. This is the simple circuit diagram for the single phase half wave controlled rectifier for R load. The only difference is here we are using not diode but we are using the thyristor. As we know that the thyristor will conduct only when we apply the positive biasing or when we apply the positive voltage, plus we have to apply the gate signal. That means here we need the forward biasing plus that gate signal to turn on this thyristor. While as in case of earlier uncontrolled rectification, we are using by just positive cycle, our diode gets forward bias, while as here we need gate signal plus that forward biasing. And for turning off the thyristor, we need here reverse voltage, and that reverse voltage is provided by this AC supply where we get that negative cycle, and because of that reverse voltage our thyristor gets turned off. Source voltage Vs is equal to Vm sine of omega t. This is one thyristor. The voltage across thyristor is Vt1. This is our resistive load, and the current across this load is I0, and the voltage across this load is V0. Similar to the previous diagrams, we need to calculate the Vs, V0, waveforms for source voltage, output voltage, output current, and the voltage across this thyristor T1. For source voltage, this is the waveform for output voltage, output current, and this is the voltage across the thyristor T1. As we know here, from 0 to alpha, where alpha is our triggering angle. We can define the firing angle as the angle that gives the largest average output voltage or the highest load voltage. We can also define it as the angle measured from the instant, that means from the instant the SCR gets forward bias to the instant it's triggered. That means here the forward biasing starts from the zero crossing, while and this SCR is triggered at this angle alpha. That means this is the our firing angle. That means in this is a driving force. That means this is the source voltage having the positive cycle and the negative cycle. During this positive cycle, from 0 to alpha until this thyristor is triggered, that means no doubt we have forward biased this thyristor at the zero crossing, but this thyristor will not conduct until and unless we have provided that gate signal, and that gate signal we are applying at an angle of alpha, and from that triggering angle or gate or firing angle, our current will flow across the load. The peak of the current will be at omega t is equal to pi by 2, and the voltage V naught the output voltage will follow the source voltage from this alpha to pi. Here the peak of this current I naught will be slightly lesser than this output voltage, because this I naught Im will be Vm upon R. And during this negative cycle, this thyristor is reverse bias, or we can say no current flows through the thyristor. If no current flows through the thyristor, that means the output voltage will be 0. The voltage across the thyristor, that means from 0 to alpha our thyristor is reverse bias, from pi to 2 pi our thyristor is reverse bias. Only the thyristor is forward biased or triggered from alpha to pi. From 0 to alpha the thyristor is turned off, from pi to 2 pi the thyristor is turned off. The thyristor is turned on only from alpha to pi. That means the conduction angle here is from alpha to pi. So I am showing as we know that when the thyristor is not conducting, that means the current in this circuit will be 0. The voltage drop across this resistor will be 0. The voltage across this thyristor will be when this thyristor is open, we can say the voltage across this thyristor will be exactly the same voltage that will be the source voltage. That means from 0 to alpha, as our thyristor is turned off, the voltage across thyristor will be exactly that source voltage. That's why I am showing here from 0 to alpha it's following this path. From alpha to pi, since thyristor is conducting, that means the voltage across thyristor will be 0, and from pi to 2 pi again thyristor is reverse bias, and that's why I am showing the voltage across that thyristor, it follows that source voltage. If we compare the waveforms for this controlled rectifier for R load and for uncontrolled rectifier for R load, the only difference lies here the triggering, the thyristor gets turned on only after that firing angle, while as in the previous case the diode gets turned on at this 0 crossing. Here the average output voltage, since the conduction angle is from alpha to pi, the average output voltage will be equal to 1 by 2 pi integral of alpha to pi Vm sine of omega t. Similarly, you can calculate the RMS voltage. Once we know the conduction period, we can calculate the average output voltage. We can calculate the RMS voltage or RMS current. In this case, the thyristor is reversed biased for a period of pi. That's why this circuit turn off time omega tc will be equal to pi. The average output voltage is equal to 1 by 2 pi integral of alpha to pi Vm sine of omega t d omega t. That becomes equal to Vm by 2 pi into 1 plus cos of alpha. That means by changing this value of alpha, we can get that variable output voltage, and the maximum output voltage will be at alpha is equal to 0. That means at alpha is equal to 0, the maximum average output voltage will be equal to Vm upon pi. Here the thyristor is conducting from alpha to pi, or we can say the conduction period is from alpha to pi, or the conduction angle is pi minus alpha. Now, the extinction angle is the angle up to which the thyristor is conducting. That means this beta will be, as the thyristor is conducting up to this angle pi, or we can say the extinction angle here is equal to pi. Here, the peak inverse voltage is equal to minus V m, or circuit turn of time is equal to 2 pi minus pi, that is equal to pi. Now, I'm going to teach you single phase half wave controlled rectifier for RL load. Again, only difference here is we have replaced that diode by the thyristor. These are the waveforms for source voltage, voltage across thyristor, output voltage, and the output current. As we know that the current flows only when the thyristor gets triggered at an angle of alpha. That's why I'm showing here the current, and the peak of the current will lie, because of this RL load, the peak of the current will lie somewhere between pi by 2 to pi. That's why I'm showing here the pi, and the current will be zero beyond the pi. The current falls beyond pi because of that inductive load, as current lags behind the voltage. Higher the value of inductance, higher will be this beta. Whenever this thyristor will be triggered, it will follow the output voltage and will continue until and unless the current becomes equal to zero. Since here current flows from alpha to pi plus alpha, we can say from alpha to pi plus alpha, our output voltage will follow our source voltage, and because of this negative part, our average output voltage gets reduced. And to prevent that decrease in output voltage, we need to add that freewheeling diode across that load. That is the next topic. We can say that the conduction period is from alpha to beta, or we can say here the average output voltage is equal to 1 by 2 pi integral of alpha to beta Vm sine of omega t dt, as the conduction period is from this alpha to beta. Beta is the point where our current across the thyristor becomes equal to zero. We know that from 0 to alpha, the thyristor is reverse biased, or we can say thyristor is in forward blocking mode. That means from 0 to alpha, follow the source voltage. From alpha to beta, the voltage across thyristor will be zero, because the thyristor is conducting from this beta to 2 pi. The thyristor is in reverse blocking mode, or we can say it will follow that reverse voltage. That's why I'm showing from this to this. From this 2 pi, again from 2 pi to 2 pi plus alpha, again the thyristor is in forward blocking mode, as this is the start of the next cycle. That means that's why I'm showing here it's from 2 pi to 2 pi plus alpha. It's following this forward, it's following that source voltage. That means these peaks are due to the forward blocking mode of thyristor, and the below peaks are because of that reverse blocking mode of the thyristor. Conduction period is from alpha to beta. You can calculate the average output voltage, you can calculate the average output current, or RMS voltage, or RMS current. Right? Because of this RL load, we get that negative peaks in the output voltage. To reduce that, we are using freewheeling diode. Because of that freewheeling diode, our input power factor is improved, load current waveforms are improved, load performance is better, or we can say the converter efficiency gets improved by using that freewheeling diode. My next topic is single phase half wave controlled rectifier for RL with freewheeling diode. This is a simple diagram where this is the source voltage, this is the thyristor, and across this RL load we have connected that one freewheeling diode. This freewheeling diode acts only, is turned on only when this inductor starts dissipating energy, and because of that this will be negative, this will be positive. Freewheeling diode will be forward biased, and the current will flow across this path, will be dissipated across this resistance. No current flow across this thyristor. This thyristor is reverse biased. And these are the waveforms for source voltage, gate current, output current, V naught, IT, and current across the freewheeling diode. Since this is the driving force, the waveform for source voltage will be like this. Here the thyristor is triggered at an angle of alpha. Here the thyristor conducts from alpha to pi, and that's why I'm showing here that the average output that the output voltage will follow to the source voltage up to the angle of up to pi only, because after from pi to this angle where our current ceases, our freewheeling diode comes into action, because of that freewheeling diode, that negative part of the output voltage gets removed. Similarly, in the second cycle also, the output voltage will follow the source voltage from 2 pi plus alpha to 3 pi. Here the thyristor conducts only from alpha to pi, or we can say 2 pi plus alpha to 3 pi, while as the freewheeling action only takes place in this period. That means from pi till our current becomes equal to 0. That means from 0 to alpha, our SCR is reverse bias, or in forward blocking mode. From alpha to pi, our thyristor comes into action, and from pi to this from this pi interval till our current becomes 0 at this beta, our freewheeling diode comes into action. Similarly, in the next cycle, thyristor is triggered at an angle of 2 pi plus alpha. Our output voltage will flow from 2 pi plus alpha to 3 pi. Similarly, the current will flow from 2 pi plus alpha to 3 pi, and the freewheeling diode will act from alpha is equal to 3 pi to this to this period where our current ceases. Since here the conduction period, of thyristor is from alpha to pi, the average output voltage will be equal to 1 by 2 pi integral of integral from alpha to pi Vm sine of omega. I'm going to show you one more diagram. That's also the freewheeling diagram. That's also the diagram of freewheeling diode. The only difference here is inductor is not fully discharged, or we can say the next cycle starts before the inductor gets fully discharged, while as in the previous case I'm showing that inductor gets fully discharged. Both can be the cases, because this beta angle depends on the in value of inductor. Higher will be the value of inductor, higher will be the value of beta. Here in this case inductor is fully discharged before the next cycle starts, while as in this case inductor inductor is not fully discharged before the next cycle starts. That's why I'm not showing anywhere here there is this zero current. I'm showing some small, that means here the thyristor conducts from alpha to pi, and the freewheeling diode from pi to this 2 pi plus alpha. Again, the thyristor conducts from 2 pi plus alpha to 3 pi, but the freewheeling diode conducts from this 3 pi to this 4 pi plus alpha. And this both the diagrams are correct. The only difference is that here the inductor is not fully discharged, while as in the previous case the inductor is fully discharged. Here the diode current will flow from this pi to 2 pi plus alpha, or we can say this next cycle from 3 pi to 4 pi plus alpha, and the current for the thyristor flows from only alpha to pi and 2 pi plus alpha to 3 pi in the two cycles. The output voltage in both the cases from alpha to pi, or 2 pi plus alpha to 3 pi, and during this free, that means from pi to 2 pi plus alpha, the output voltage is 0, because of the freewheeling action, because of this freewheeling diode, as no current as the whole current flows through this path and no current flows through the thyristor. The next load is RLE load. That's one more inductive load. Again, for control rectification, we are using diode. We are using thyristor instead of that diode. The waveforms for this circuit is, these are the waveforms for this circuit. Here this represents the source voltage, the gate current. This represents the V naught. This is the current. This is the voltage across the thyristor. That means here the thyristor will conduct only when the Vs is equal to voltage across source is equal to voltage across inductor plus voltage across resistor plus voltage plus EMF E. Here this E in the load may be due to the battery or a DC motor. From 0 to theta 1, this thyristor cannot conduct as the EMF is greater than the source voltage, or we can say the thyristor can conduct only when this alpha is greater than theta 1. For alpha less than theta 1, thyristor cannot conduct. We are giving the firing pulses at alpha, and this alpha is greater than theta 1. That means that thyristor will conduct from this alpha from this alpha to this beta, as current flows beyond this pi due to the inductive load. And after that the output voltage will follow the source EMF, because from 0 to alpha the thyristor is reverse biased in the forward blocking mode, and from this beta to from this beta to 2 pi plus alpha, again the SCR is in reverse blocking mode. That means from 0 to alpha, SCR is not conducting. From beta to this 2 pi plus alpha, again SCR is not conducting. From this 2 pi plus alpha plus beta to 3 pi, no SCR is conducting. This is the current that's flowing from alpha to this beta. At this point, the output voltage across thyristor will be equal to reverse voltage or back EMF, or this EMF E. From this interval, from 0 crossing till that theta 1, since our source voltage goes on increasing, that means voltage goes on, this reverse voltage goes on decreasing until at this theta 1, this source voltage becomes equal to E. But now the thyristor is forward biased but is not triggered until, because we are providing the triggering angle at that alpha. That means from this theta 1 to this alpha interval to this period, from this theta 1 to this period where we are providing the gate pulse, there will be a forward voltage across the SCR. From this alpha to beta, SCR is conducting. After that, since SCR is triggered off, the reverse voltage across this SCR will be equal to it will follow that source voltage, and the peak of this voltage will be equal to minus Vm minus E. This is basically minus into bracket of Vm plus E. Again at this interval, that means 2 pi interval, that means this is a 0 crossing of the next cycle, the output voltage will be equal to that EMF E or minus E, and it goes on decreasing because source voltage goes on increasing. Again this is the same part, and the next and the SCR will conduct from this 2 pi plus alpha to this 2 pi plus alpha plus beta. That means up to this period our SCR will is turned on, or we can say voltage across thyristor is 0. Here the circuit turn off time is time will be equal to 2 pi plus theta 1 plus theta 1 minus beta, and the average output voltage, since the thyristor is conducting from alpha to beta, average output voltage will be equal to 1 V naught is equal to E plus I naught into R, or we can say that V naught is equal to 1 by 2m Vm into cos of alpha minus cos of beta plus E into 2 pi plus alpha minus beta.